Hi, everyone. My name is Kelly Greenlee. I am the Community Outreach Librarian at Prince Memorial Library. This event is brought to you this evening by both Prince Memorial Library and Falmouth Memorial Library. We are teaming up on this event to, to bring this to you. Sorry, I just lost my screen. There we go. So we're very happy that you're here this evening. And it's my pleasure to introduce to you Dan Marks. He is the Wastewater Superintendent for the town of Falmouth. Prior to working for Falmouth, Dan worked for 12 years as an engineering consultant for wastewater utilities around New England, helping to design and construct wastewater infrastructure around the region. Dan lives in North Yarmouth with his family, and we just want to make a note here that Cumberland, if you're coming to us from Cumberland, Cumberland's sewered areas are pumped to Falmouth for ultimate treatment as well. So that's an important distinction to make because maybe people in Cumberland are wondering, why are we listening to the Falmouth guy? And that's why. Thank you, Dan, for doing this, and welcome. And I'm going to pass the reins to you.
Well, thank you for the introduction. And let's see, I'm gonna close that on my screen here. Okay. Yes, so thank you for joining me this evening. As Kelly mentioned, my name is Dan Marks. I am the superintendent of the wastewater department in the town of Falmouth. And as was mentioned, we treat wastewater generated in the sewered portions of Cumberland and Falmouth. And we also receive septage from the unsewered areas of the towns. And I love talking about wastewater. And I know that makes me a little weird. So I thought I would start by telling you why I wanted to give this talk and hopefully get you excited about it too. Most of us do not think about what happens after we flush or after water goes down the drain. And this is what we call flush it and forget it. This paradigm evolved over many generations and centuries, and for good reason. So I want to start by going way, way back for some context setting. Before we knew about microscopic pathogens and their presence in our waste, people were getting very sick and dying from all kinds of nasty things. Cholera, dysentery, typhoid. Chamber pots were emptied into the streets and gutters. Enter the toilet. I am biased, but probably one of the greatest public health interventions of the last millennia. Deep pits, and then later on piping networks, separated us from our waste and saved an uncountable number of lives. This will not be the focus of my talk tonight, but it is worth noting that according to the World Health Organization, over 1.5 billion people still today do not have access to basic safe sanitation services. So our flush it and forget it mentality has evolved over a long history. Yet we are in a new time where this mantra is not serving us anymore. Not the least of which is that the modern toilet literally flushes away clean drinking quality water. But more to the point of my talk tonight is that the separation between ourselves and our waste is becoming more and more difficult. In this presentation, I invite you to gain a deeper understanding of your wastewater system, its issues and complexities, as well as opportunities for better public health and environmental protection. In my experience, there are 3 broad and overlapping challenges that have the biggest impact on the future of wastewater treatment. The first, the age of our infrastructure. More than 50 years after the Clean Water Act, which is the legislation that funded a lot of the wastewater infrastructure we have today, and approaching 100 years after many of our sewers were installed, incredible costs are mounting, and our residents and users need to be aware of the investments that are needed to maintain the systems. The second point is climate change. Much of our infrastructure is located in low-lying areas. You may be familiar with the saying, it flows downhill. I'll keep it PG. My kids are on the screen here. But there's an expression about it flowing downhill. So that is where we are. Climate pressures are driving resiliency needs and adding to the significant investments that are needed. And finally, pollution, covering everything from the need to maintain nutrient balances in the environment, for example, nitrogen in Casco Bay, to what we in the industry call contaminants of emerging concern. That could include microplastics, pharmaceutical residuals, healthcare products, and yes, PFAS and other chemicals. And we'll get into all of that. I often tell people that if they really want to understand our relationship and impact on nature, go to a landfill or go to a wastewater treatment plant and see what it is that we are wasting. For people concerned about environmental protection, I think this is a very important place to start. So I hope I've piqued your interest, and I'm happy you're here. I want to provide a little context for wastewater treatment. Why do we do it? Or another way of saying, how bad was it before we had wastewater treatment? I want to introduce you to your infrastructure that provides these vital services, starting with the pipes in the road in front of your house and all the way to the treatment plant. Important to note that all of Cumberland Seward areas, as we mentioned, are ultimately conveyed to the Falmouth Wastewater Treatment Facility. And then I want to show you what we do at the wastewater treatment plant, how we make dirty water cleaner, and how we protect the environment and public health. Finally, I want to talk about sludge. It's way more interesting than you think. Why we make it, what's in it, and maybe hint at some of the opportunities for the future. I mentioned to Kelly, if I run straight through without questions, I'm clocking at about 40 to 45 minutes, but in reality, I can talk about this stuff all day. But I do want to allow ample time for questions if anybody has them. So please fire away. So let's get started with a little interaction. I find that everyone has a relationship with wastewater, whether you know it or want to admit it. So no pressure, the stakes are low, but here's a pop quiz. So we can enter into the chat. How many gallons of wastewater do you think the average person produces in a single day? Think about all the water you use that goes down the drain. How much water would you say you use in a day? Type in either A for 25 gallons, B for 40 gallons, C for 50 gallons, or D for 70 gallons. What do you
Wow,
think is the
wow,
average?
we're way all over the board here.
D plus, I like Pat, okay. I don't know if that's like a good grade or a bad grade. Okay, great. I love the participation here. Give another couple seconds here if anybody else wants to add. Yeah, okay. Kelly mentioned I come from an engineering background, so designing systems was part of my background. And typical design guidance, I'll go ahead and continue on here, but typical design guidance for a new collection system uses 70 gallons per day per person as a minimum. Some sources suggest even using 80 or even 100 gallons per day per person. So think about how much water that we have to plan for at the treatment plant based on the number of users we have. In Falmouth, our average daily flow at the treatment plant is around 800,000 gallons per day. And between Cumberland and Falmouth, we have around 3,500 Seward connections serving almost 9,000 people. This makes about 90 gallons per person per day in Falmouth. Collection systems also need to be designed for infiltration. So that 800,000 gallons per day at the treatment plant includes infiltration, which is basically the groundwater and stormwater that enters the sanitary sewer system. Infiltration increases as the system ages, and this is why maintaining the collection system and performing strategic capital improvements is critical. Thank you all for participating in the first pop quiz here. So let's go on a brief history, talk about the histories of wastewater treatment. As I mentioned earlier, I think the toilet is one of the greatest advancements in public health ever. The sewer got us some distance from our poop and pee. Sewer discharged into the closest water body. The problem with that, as most of us are aware, and famously the Cuyahoga River in Cleveland, which caught on fire many times and drove what we needed, what ultimately became the Clean Water Act. Closer to home, these photos were taken in June 1973 as part of an EPA effort to photo document the condition of water bodies before the Clean Water Act went into effect. On the left, you are looking at sludge floating on the river, on the Androscoggin River, above the Gulf Island Dam near Lewiston. And on the right is effluent from the Jay paper mill that was discharged directly into the river without adequate treatment. In Falmouth, we discharge into the Presumpscot River, in the tidal estuary of the lower Presumpscot. Here's the Presumpscot in Westbrook. This photo is of the Haskell Silk Mill in Westbrook around 1901 or 1902. Sawmills and cloth mills lined the lower river, and dams made the pollution worse as it stagnated the water. Organic pollution fed microscopic life that decomposed, and in doing so, consumed all the dissolved oxygen, leaving nothing left for aquatic life and creating a dead zone. People who remember that time and talk about the Presumpscot River talk about it, the river being a caramel color with huge amounts of foam and smelling horrible. So enter Edmund Muskie, who spearheaded drafting the passage of the Clean Water Act. He's famously from Rumford on the Androscoggin. The first Federal Water Pollution Control Act was written in 1948, but it took its current form in 1972 with amendments that came to be known as the Clean Water Act. So what changed with the Clean Water Act? First, lots of money from the federal government, up to 90 cents on the dollar funded from federal grants to build infrastructure, piping networks, and treatment plants. So that's the 50 years ago that most of this infrastructure is now at 50 plus years old. In Falmouth, sewers under the streets drains directly into the ocean. So the picture I'm showing here is the Foresight Interceptor Plan. You're seeing Town Landing Road and some of the adjacent roads. Prior to the Clean Water Act, those sewers that existed under those streets just discharged directly into the ocean. The Clean Water Act funded what we call interceptors, which interceptor sewers, which intercepted those street sewers before they dumped into the ocean and rerouted that flow to the newly built wastewater treatment facility. The town of Cumberland was sewered at a later date after the Clean Water Act was enacted. The Clean Water Act also importantly set up a system of waste discharge licensing. Now all the facilities discharging into the waters, quote unquote, waters of the United States must hold a license to do so. Our wastewater discharge license in Falmouth and others defines the parameters and maximum pollutant concentrations that we are allowed to discharge and the testing we must do to certify we are meeting our license. Now that I've provided a very brief historical background, let's talk about wastewater in more detail. What is it? You'll notice that I put the word waste in quotes. It's another paradigm I'm trying to change, and one of my favorite quotes is up on the screen. Pollution is nothing but the resources we are not harvesting. We allow them to disperse because we've been ignorant of their value. This table lists a range of nutrient value in wastewater. In our bodies, as we metabolize food, we extract nutrients from our food. The cells and bacteria in our body grow, multiply, and die, and become part of what we excrete. On average, adults are in a nutrient steady state, where the amount of nutrients we take in from our food are roughly equivalent to the amount of nutrients in our excreta. We measure organic matter in terms of biological oxygen demand. So what is BOD? It's an important parameter in wastewater systems. It is a measure of the organic strength of the wastewater and was one of the primary pollutants that the Clean Water Act regulated. We measure it as oxygen demand because as bacteria consume organic waste, they also consume oxygen. BOD is a measure of how much oxygen is needed for the bacteria to metabolize the waste that we're feeding them. As a backyard gardener, it has struck me that what we consider waste at the wastewater treatment plant is what farmers and gardeners call fertilizer. So effectively, this table is showing the NPK value of wastewater. It's interesting to me to note that the majority of the nutrient value in wastewater actually comes from our urine. The nutrient content of urine produced by Americans each year could replace 9 billion pounds of chemical fertilizer. Considering that we are approaching end phosphorus and the vast amount of energy we use to synthesize nitrogen fertilizer through the Haber-Bosch process, this becomes a significant consideration. The urine produced in one day by an adult contains enough fertilizer to grow the wheat needed in one loaf of bread. So you could actually fertilize the land to grow food. And with right now we're calling that waste. These facts are from the Rich Earth Institute in Vermont, a research organization that studies the use of human urine as a fertilizer. So I want to take a minute here and get some more involvement from you all. This table is showing the organic matter and nutrients that that wastewater is composed of. But what's not listed here? Or in other words, what else is in our wastewater besides these nutrients? This is not a multiple choice. I'm looking for some creative options here. Emerging contaminants. COD. Oh, we have a chemist here. Okay. That's good. Bacteria. Yep. Plastic. Very good. Medicines. Okay. Nailing it. You guys have thought about this. PFAS. Okay. Yeah. I mean, you've covered the big things that I wanted to mention, but in general, I guess I'll say it's everything that we wash or flush down the drain. So if it goes down the drain, then it ends up at the wastewater treatment plant. We are not in control of what else is in our wastewater. So yes, we have an NPK fertilizer value of wastewater, but we also have all this other contamination that we need to deal with. Great. Thank you for that participation. Okay, so now let me introduce you to your local collection system. I know you won't be able to read the details on these maps probably, but hopefully you'll be able to recognize the shapes. The large green area in the middle is the Valhalla Golf Course in Cumberland. So Cumberland has almost 1,300 sewered connections, 25 miles of sewer in the town, 13 pump stations, and 8 miles of pressurized force main coming from these pump stations. The system is owned by the town, but under contract, it is operated by the Portland Water District. The extent of it, starting in the northwest on Crystal Lane and Shady Run, they drain down to Greeley Road, which runs down Valhalla Road, picks up Pinewood and the side streets, a little bit of Main Street near the school, the MS 8051 school complex. There's a short section of sewer down Main Street south of Tuttle Road, including a library that happens to be in that location. Also Drown Road, and all of that flow drains to Tuttle Road and then is pumped east on Tuttle Road. Here's another series of maps. I don't know if you can all see my mouse, but here's the Tuttle Road force main comes across, hits Middle Road and goes north on Middle Road. And then it goes under the highway, under I-295 at the end of Greeley Road. The northern extent of the Cumberland collection system is on Fern Lane. There's also a pump station on Ledge Road, picks up the Thomas Drive neighborhood across from the Shabig parking lot. All that drains to a pump station on Powell Road, which is pumped up to the height of the land on Route 88. And then from Route 88, it drains by gravity down Route 88 to the Foreside Road pump station. I'm showing this map split in half. The left side is north and the right side is south. And then into Falmouth on Route 88. On Route 1, we pick up the new units on Casco Bay Drive, neighborhoods on Granite Ridge and Falcon Drive, and then into Falmouth on Route 1. So all of the sewered areas of Cumberland drain either down Route 1 or Route 88 and enter into Falmouth in one of those two locations. In Falmouth, we have almost 2,200 sewered connections. We have 44 miles of sewer. We have 33 pump stations and 14 miles of pressurized force mains coming from those 33 pump stations. The sewer system in Falmouth is also owned by the town, but it's also operated by the town. That's the department that I am a part of. We operate the Falmouth collection system and treatment facility. The Falmouth collection system actually also starts in Cumberland. There's a small section just over the line on Wynn Road in the Falmouth Country Club area. So we collect sewer from all of Falmouth Country Club on Wynn Road, goes down Wynn Road, portions of Route 100, Exit 10 area, Layton Road, and all that is pumped on Falmouth Road up behind the high school in Falmouth, through the Woodlands, and all of the Woodlands neighborhood is on sewer as well. The Woodlands, from the Woodlands area, it flows down Woods Road to Middle Road and then south, picking up some of the side streets there. The southern part of Middle Road, which is Route 9, we pick up, our southern extent is on the Pleasant Hill area. That is pumped up to Lunt Road, and all of the sewer from the west side of 295 goes under the highway on Lunt Road. We have a pump station on Lunt Road that pumps to the treatment plant. East Falmouth, basically all of Route 1 and the Route 88 corridors and the side streets are sewered. The main interceptors were built as part of the Clean Water Act. The street sewers that exist on some of the side streets that dumped into the ocean and some of the other water bodies predated the Clean Water Act. We drain our systems by gravity to the maximum extent possible, and then we need to pump. Our pump stations are always in low-lying areas, often in environmentally sensitive areas, often at risk to climate change pressures, such as sea level rise, storm surges, and increased precipitation. On the upper left, you may recognize this if you've driven through Lunt Road. You can see I-295 in the background on the upper left picture. That's our Lunt Road pump station that pumps everything from West Falmouth. It sits within the Skiddery-Gusset Creek drainage. And below that and on the right is our largest pump station at Mill Creek on Route 88. All of Cumberland's flow goes through the Mill Creek pump station. The upper level, which you can see the outside of it on the bottom left, houses our power and control panels, motor drives, and a generator. But let me briefly take you inside this pump station. 3 stories below the surface, it is a concrete bunker. There are 4 electric pumps there, and at least one of which is always running. There are 2 30 horsepower pumps in the middle for normal dry weather flows and 2 60 horsepower pumps for wet weather flows. The wet well is just on the other side of this wall here, if you can see my mouse, that's where all the water from Cumberland and the Foreside Road in Falmouth collects there. And then the pumps are piped through that wall and then discharge up through the ceiling. and underground to the treatment plant. This is an extensive network of piping and mechanical equipment and requires everyday maintenance and review. But on top of that, we have a number of issues that are presenting themselves. As I mentioned, the age of the infrastructure. Much of our infrastructure is 50 years old. And inevitably, when we experience failures, has to be during a holiday weekend. The picture on the left is of my 8-year-old running a construction site. Not really, but it was it was over the Christmas holiday, so he came with me. And but in the trench and section behind him is a section of asbestos cement pipe that was installed probably in the 1950s. Asbestos cement pipe, or what we call AC pipe, is particularly sensitive to the sewer gases that can build up in long piping networks. This AC pipe collapsed, it flooded someone's basement, and required over $100,000 in emergency repairs. So, Happy New Year. The picture in the middle is a manhole below Shoreline Drive in Falmouth, where we have another interceptor that runs below the beach. And the picture on the far right is our Underwood pump station, located near the old Underwood Spring below Foreside Road. You can imagine how these and related pieces of infrastructure are impacted by climate change pressures, including sea level rise and storm surges. The age of the infrastructure and climate change increase the infiltration and inflow, basically the leakiness of our system. And we are constantly battling that infiltration to maintain capacity at the treatment plant. Our discharge license, again, that came from the Clean Water Act, specifies that our average daily flow allowable is 1.5 million gallons per day. Ideally, all of that flow would be dirty sewer water that we can treat. But every gallon of relatively clean stormwater or groundwater that enters the system takes the place of a dirtier gallon that we could otherwise treat. And maintaining capacity in our system is a critical component for the long-term health of the community. As I mentioned, on a normal dry day, we see around 800,000 gallons of flow. However, during heavy rain events and ground melt in the spring, this time of year, we can see over 5 million gallons in a day. This is an indication of the leakiness of our collection system. In other words, we are paying to treat infiltration and inflow to the same standard as dirtier wastewater. Okay. All that to get us to the treatment plant. So we finally get to the wastewater treatment facility. The Falmouth Wastewater Treatment Facility is located on Clearwater Drive, behind the Walmart and near the University of Maine Cooperative Extension. The treatment plant can be thought of as a series of barriers between the waste we produce and nature. Wastewater treatment combines biological, physical, and chemical processes. We are modeled after nature, utilizing microbial communities to consume contamination. We do what nature does, except that we speed it up using vast amounts of energy so that it can be located in a smaller footprint. You'll hear me say this a couple times tonight. We are farmers, and microbes are our herd. And just like a farmer, we have to keep what we are growing happy. Our microbes must have everything they need to thrive: food, oxygen, and nutrients. But before we get into that, let's step through the treatment process. The first stop is the headworks, where all of the influent from our collection system comes. So here's the headworks. In the headworks, we use physical processes to remove things that cannot be treated through the biological process. This is our first set of barriers between our waste and nature. Inside the headworks, on the left is our automated bar screen. This equipment removes any non-organic insoluble material that our biological system can't treat. Think plastic bags, bricks, anything that can be flushed or drained down a sewer. And on the right is our grit removal system. We pump air into a large tank, and this drops all of the heavy suspended inorganic solids out to the bottom. Think sand and gravel. It is then conveyed with a screw up into a dumpster. You might not be able to see it, but that in the right-hand side picture, there's a yellow shroud in the back. That's the motor. And inside the gray compartment in front of it is a long screw. It's about 30 feet long. It goes down about 20 feet deep into this tank and pulls the grit that drops out of the water column up in a screw and dumps it into a dumpster. The grit can prematurely damage our mechanical equipment further downstream, so we try to get rid of it. We truck both the screenings from the bar screen and the grit to the landfill at Eco Maine. Once this insoluble inorganic waste is removed, we are ready for the next step: biological treatment. So from the headworks, water is piped to the aeration tanks. The aeration tanks are the biological heart of the treatment plant. What does this mean? Simply put, we are using bacteria to consume organic matter. In a natural environment, like a river, microbes do the same thing. Here is a close-up of our aeration tanks. There are two of them in parallel. I think you can see my mouse, so I'll say they go in this way, around the U-bend, and then back out that way. And both of them are mirrored and in parallel. At the plant, we try to optimize the environment to select for certain bacteria that efficiently consume organic matter. Bacteria and organic-rich water are mixed in an aeration basin and provided with dissolved oxygen to stimulate the decomposition of organic materials through biological oxidation. One of the primary ways we do this is to supply oxygen. You'll notice the aerated zones with the bubbles. So we aerate that water column to a certain dissolved oxygen level, about 2 parts per million. In addition to air, our microbes need the right amount of food to support the population. So a critical parameter for us is the food to mass ratio. We maintain the right population or mass of microbes to treat the organic waste that's coming to us, the food. These are the blowers that provide air to the biological process, and they are the single largest energy draw at the treatment plant. Our electric bill at the treatment plant alone is flow dependent, but it averages about $10,000 per month. Just as a side note, since we were just talking about the pump stations and collection system, the 33 pump stations we have in town average around another $10,000 per month. So we are spending a lot of energy. But at the treatment plant, these blowers providing air to the biological process are the largest single consumer. The mixture of microorganisms and wastewater is allowed to settle in the secondary clarifiers for separation of liquid and solids. A certain portion of the settled solids is returned to the aeration basins to provide the right level of microorganisms for continuous treatment. The photo on the left is one of our secondary clarifiers. Clarification is a physical process of settling. We quiet the flow and allow the biological flocks of microorganisms to settle to the bottom. Using the pumps shown on the right, we remove the settled sludge from the bottom of the clarifiers. Most of that flow, now called return activated sludge, is returned to the aeration tank to optimize the food to mass ratio. So we've started to complicate our picture a little bit. We have the raw influent from the headworks in green, and now the return activated sludge from the bottom of the clarifiers in orange. We have the air from the blowers in blue. We modify how much sludge we return to get the right amount of microbes to eat the incoming waste, and we give them the oxygen they need to consume that waste. As the microbes consume organic waste, the aeration tank is another barrier between the waste we produce and the environment. So that is how we manage our microbial herd to consume organic waste, measured as BOD. But here is our close-up of the aeration tanks again. You may also notice the zones that have no bubbles, below the green lines that I drew in. We have found that by optimizing the environment, we can also treat for nitrogen. But why do we care about nitrogen? Nitrogen is the limiting nutrient for growth of plankton and algae in marine systems. You may also see that phosphorus is a limiting nutrient for growth in freshwater systems. Excess nitrogen causes plankton and algae to bloom. And as this organic matter decays, the bacteria doing that work to decompose the organic matter use up all the oxygen in the water column, leaving no oxygen for other aquatic life. This is called eutrophication. So how can we help maintain the nutrient balance in the environment downstream of our wastewater treatment plants? To understand this, let's take a quick look at the nitrogen cycle in nature. About 80% of our atmosphere is nitrogen gas. There are bacteria in the soil, nitrogen-fixing bacteria, that convert the nitrogen gas or fix it to ammonia, or NH3. Then there are nitrifying bacteria that convert the ammonia to nitrate, and denitrifying bacteria that convert the nitrate to nitrogen gas back into the atmosphere. Meanwhile, that nitrogen in the soil is used for soil health for the bacteria for the life under the ground. So how do we use the nitrogen cycle at the wastewater treatment plant? I mentioned early on that the water environment has a nutrient balance that we work to maintain. In wastewater, most of the nitrogen is organic nitrogen. It's mostly urea from our urine. And in the collection system, urea is converted to ammonia. So in the aquatic environment of wastewater treatment, we start with ammonia, or the NH3. So let's go back to our aeration tank. Denitrification occurs in a low or no oxygen environment, what we call the anoxic zone. In the anoxic zone, nitrate acts like oxygen in microbial metabolism. Nitrification, on the other hand, is strictly aerobic, or with oxygen. But before we can have nitrate to denitrify, we have to create nitrate through nitrification. To do this, we have an internal recycle that pumps around 3 times the forward flow of the plant back through the treatment process. So just for rough numbers, if our flow at the treatment plant is 1 million gallons per day, that internal recycle, the big green arrow, may be pushing 3 million gallons a day of flow. So that what's racing around in each of those tanks is actually 4 million gallons per day on a flow rate. What this allows us to do is get the nitrate-rich water that has been generated by nitrifying bacteria during the aerobic decomposition of the organic matter, combining that with the organic-rich influent water that's coming from the headworks. This feeds the denitrifying bacteria that prefer a low oxygen environment, where nitrate, instead of oxygen, is used as the terminal electron acceptor in the microbial metabolism. The result is that we off-gas nitrogen, N2, back into the atmosphere. So nitrogen removal in our aeration tanks is another barrier between our waste and nature. And as I mentioned, we're farmers, we're microbe farmers. So we saw what we did with the sludge from the bottom of the clarifiers. Now let's follow the overflow, or what we call the liquid train. This picture shows the clear water flowing over the weirs at the outlet of the clarifier. The last barrier after clarification is disinfection. This is a chemical process. We disinfect with sodium hypochlorite, bleach, to ensure that we kill any pathogens. We store this in a 1,500-gallon tank shown on the screen. We also remove residual chlorine before we discharge into the receiving water. It may be obvious, but we can't discharge chlorine-rich water into the environment without killing the natural microbial life. Can you all still see my screen?
Yes.
Okay, sorry, something changed with mine.
No, you're good.
Okay. Let's see, Zoom slideshow. Sorry, let me get back here to my piece. Okay. So I was saying we can't discharge chlorine-rich water into the environment without killing the natural microbial life. So we neutralize the residual chlorine with sodium bisulfite. Both chemicals are metered into the clarifier effluent based on flow rate and residual chlorine. Okay, great. Chlorine needs time mixed with the water to make sure that pathogens are killed. We do this in the serpentine tank that ensures the chlorine has sufficient contact with the water. We measure chlorine residual at the head end of the tank to make sure we are putting enough chlorine in. We measure residual at the end of the tank to make sure all of the chlorine has been removed before we release it back to the environment. All of the clean water from the treatment plant is discharged into the tidal estuary of the Presumpscot River. This means that water that was sent down the drain on Greeley Road in Cumberland has traveled almost 11 miles underground in pipes before it is finally discharged back into the environment. On average, we remove around 98% of the organic matter in the water, as measured by BOD, and 98% of the total suspended solids. And we achieve on average 80% removal of nitrogen. I'll make one other quick note on climate change. You are seeing here our outfall head wall, which has been undermined through tidal action and higher sea levels since it was installed in the mid-1980s. And we are currently working on relocating this outfall further upland. Another quick note on chemical pollution. Following the Clean Water Act, as I mentioned, our wastewater treatment plants were primarily designed to treat for organic waste, as measured by BOD, and total suspended solids. And as I mentioned, we do a very good job at doing that. Some plants treat for heavy metals if needed based on the users in the collection system. But more recently, plants have been upgraded to treat for nutrients such as nitrogen and phosphorus. What I hope is clear is that today's wastewater treatment plants were not designed to treat for PFAS, pharmaceutical residuals, or many of the contaminants of emerging concern. Part of the opportunity of wastewater treatment for better public health and the environment in the future is based on the fact that we have a collection system that goes to everyone's home and literally takes your waste away. So even though we are diluting our waste by adding clean water to it, we are centralizing your waste by collecting it at the treatment plant. Because the wastewater treatment plant is a barrier between the pollution we create and the environment, we can bolster that barrier by adding new processes that treat the contaminants of our modern consumption lifestyle. This comes at a cost, however, that must be balanced with the costs of maintaining our existing infrastructure and everything else in life. Okay, but we're not done yet. That was the liquid train. Now let's get back to what we call the solids train. Because the quantity of activated sludge is always increasing through the continual reproduction of the microorganisms, excess sludge must be removed or wasted from the process. How much sludge we waste versus how much we return to the aeration tanks sets what we call the solids retention time, or SRT, another critical wastewater treatment parameter. To accomplish this, sludge is periodically pumped out of the system to holding tanks. It's now called waste-activated sludge. On the left, here are the pumps from before that pull the sludge out from the bottom of the clarifiers. As we saw, some of that sludge is returned to the aeration tanks, and some is wasted, which is pumped to these two tanks shown on the right. And here's our aerial view again, showing how those pipes go. We must waste sludge to prevent the biological overload of the secondary treatment process and subsequent loss of solids through the plant discharge. In other words, if we didn't make sludge, the sheer mass of bacteria that we're growing and holding at the treatment plant would be washed out and would end up in the environment. Sludge is pumped into the storage tanks at around 1 to 1.5% solids. Think of very thick coffee as a consistency. In the storage tanks, biological activity increases the solids content slightly through digestion of volatile solids. However, this is still very much a liquid. Therefore, the final step of the sludge journey at the treatment plant is dewatering, which is shown in the aerial photo here. There are a few different technologies that can accomplish sludge dewatering. In Falmouth, we use a centrifuge, which essentially spins the sludge at a very high velocity to wring the water out. With this dewatering process, we increase the solids concentration to about 20%. That's the piece of technology, the equipment that's on the left-hand side of the screen. At this point, our sludge looks like slightly wet compost, but it would be recognized as solid. We use conveyors to load the sludge into the dumpster. In Falmouth, we load a little more than one dumpster each week. And over the course of the year, we produce about 800 tons of sludge. So now that our sludge is in a dumpster, what do we do with it? And I have a couple more slides on sludge disposal, but I want to check in. I see that there's a couple things in the chat. I have 15 more minutes. I could run through sludge disposal and what we do with the sludge pretty quickly. Let me see what's in the chat. I'm having some issues with the Zoom here, Kelly. I'm not sure if you can tell me what's in the chat.
The chat is just saying you're doing great, Dan.
Oh,
we do have one. We have one question here. Any chance of installing solar panels at the treatment plant?
That's a great question. We do have some land. Let me go back to, can I go back here? Just you can see from this aerial photo, we do have quite a bit of land. We are in the shoreland zone, so we're somewhat limited from a permitting perspective. And we do have, you know, the site may look like it has a lot of open space, but as you can imagine from some of the arrows and pipes that I've shown flowing from one building to the next, there's a lot going on underground here. So we can't put stuff over. but we have a lot of flat building roof, and we do have areas where there's no piping or nothing else that would get in the way. So we are, and this is common for wastewater treatment facilities, we're the largest energy consumers in the town. That's common in most municipalities where there are wastewater treatment facilities. So it would make sense to produce electricity where we're consuming it. It is something that we're talking about at the town. You probably are aware that the town has recently installed a solar array on the old municipal landfill on Woods Road. So balancing, that does offset some of our electrical costs. But there's more to be done there. We're looking into it. It's an option. It's an opportunity for sure.
Okay, so people are at the edge of their seats. They want to know what happens to the sludge.
Okay, great. Well,
And somebody's asking about EcoMain's incinerators that cannot destroy PFAS, so what do they do with the sludge?
great. I will definitely get into that a little bit. I have a couple slides on PFAS, one slide on PFAS destruction, some promising technologies. Just to clarify, we do not send our sludge to EcoMain. We send the inorganic material from the Headworks building to EcoMain. So that's our grit, like the sand and gravel, and insoluble materials like plastics that might end up, not microplastics that make it through the screen, but that bar screen or Headworks takes out plastic bags and larger plastic things that you might imagine are in the sewer system. That's what we send to EcoMain. But so let me go on then. We can talk, I'll go through these next couple slides and we'll save some time for questions about sludge disposal. Okay. So what do we do with the sludge after we dewater it? Prior to the discovery of contaminated milk on a farm in southern Maine, which many of you may have heard about, and going back to the 1970s, most sludge was, quote unquote, beneficially reused by land application. This solved our sludge problem and was a source of cheap fertilizer for farmers. Beneficial reuse was promoted by the US EPA and the Maine DEP. In 2021, Maine led the nation by banning the land application of sludge due to the presence of PFAS. Some other states have followed suit, but really the whole nation is watching what we do in Maine on this issue. For those that don't know, let me just quickly say, what is PFAS? It's per and polyfluoroalkyl substances. They're used in various consumer products for their water stain and grease resistant properties. Think Gore-Tex jackets or Teflon and other nonstick cookware coatings, stain-resistant furniture and carpets. It's also in many cosmetics, clothing and shoes, soaps and waxes, contact lenses. The list is very long. It's a family of thousands of chemicals, and the common element is that they have a carbon-fluorine bond backbone that is known to be one of the strongest bonds that can be made in chemistry. Thus, they have been called forever chemicals. They were first introduced in the 1940s. They have been found in polar bears in the Arctic and rainwater. PFAS are ubiquitous, and they are also in sludge. Now that we no longer land apply sludge, the landfill is our only option. This picture is showing the Juniper Ridge landfill, which is just north of Bangor in Old Town, where the vast majority of the sludge produced at the wastewater treatment plants of Maine end up, including the Falmouth sludge and the Cumberland sludge. So once a week, we get, or thereabouts, we get that dumpster picked up out of our dewatering sludge bay, and it's hauled to Old Town to dump it in the Juniper Ridge landfill. But what happens to PFAS in the landfill? As rain falls on the landfill, chemicals, including PFAS, end up in the landfill leachate. Leachate is usually pumped to a wastewater treatment plant, if we're lucky. If it's a lined landfill, and Juniper Ridge is, it ends up at a wastewater treatment plant, where PFAS ends up again in the wastewater treatment plant sludge and back at the landfill. So this is clearly not a sustainable solution. We're effectively accumulating PFAS in the landfill leachate, and then the treatment facility. But this is what we're doing at the present moment. It's further exacerbated by the fact that the landfill has a finite capacity. That's the source of much debate, and there's a lot of politics behind that. I'm happy to talk about that more, but I'll continue on here for now just to get through the slides. Here's an article from the Maine Sunday Telegram from March of 2023. From Maine to California, the solution to sludge is not settled. In fact, the disposal approach in Maine, banning the spread on farmland because of PFAS risks, directly opposes the tack taken by eco-conscious California. Effectively, what California said is we don't want organic material in our landfills. And the table on the right shows why. This is from the Biosolids Emissions Assessment Model, or BEAM. This model includes the most common typical sludge end uses, and it calculates emissions based on factors of from the UN Intergovernmental Panel on Climate Change. It combines methane, CO2, and nitrous oxide into a CO2 equivalent per ton of organic material. And effectively, what this model shows is that sludge in the landfill is a carbon source in the atmosphere, while land application of sludge acts as a carbon sink. This is because organic material in a landfill creates methane. Carbon put back onto the soil and properly managed will stay in the soil. Of course, that was why it was deemed a fertilizer, that and the nutrient value, why it was deemed a fertilizer by farmers and EPA before we had the concern over contamination. In Maine and in California, both states are trying to do the best they can to protect their citizens and the environment. The reality is, at present moment, we are choosing protecting our farmland and the food that comes from it, or protecting the climate and the air we breathe. I hope that we will not have to make that choice someday. So let me get to one thing I see as an opportunity. In response to the sludge disposal need, technologies are being developed that theoretically have the ability to destroy PFAS. Someone mentioned incineration earlier, and that is correct. There's, in my understanding of the research, there has been a lot of research on incineration. It can destroy that carbon-fluorine bond, but it's difficult to maintain a consistent temperature across the burner in an incinerator to get it to a consistently high enough temperature to break that bond. But here I'm showing two promising technologies that are being studied. Oh, I need to shut my slide again. I had some issue with the presentation here. Okay, great. So on the left is the pyrolysis process. This is currently how we produce biochar. Pyrolysis is the heating of organic matter, but in the absence of oxygen. So it's not combustion, it's the absence of oxygen. Some companies have developed technologies to make biochar with sewage sludge. The other promising technology that I'm highlighting here is called supercritical water oxidation, which is at extremely high pressures and temperatures, water enters a fourth state. It is not solid, liquid, or gas. It appears like something like a vapor. With both of these technologies, the promise is that the very strong carbon-fluorine bond will be broken. And in doing so, the other contaminants in the material will be reduced to their elemental state. If we are doing that with PFAS, because it's such a strong bond, then we are also breaking the bonds of other chemicals, such as contaminants of emerging concern. This is all unproven at this point, and I should mention that the technologies are not in like industrial scale readiness. These are all, they're being piloted. Some of them are being piloted, but they're not ready for mass deployment. And as you may imagine, all of this stuff is very, very expensive. So we need to come to some consensus, and this is one of the reasons for me wanting to do this talk, that this is a priority. The science is evolving on this. The toxicity of PFAS is something that we're still understanding more and more. But the protection of the environment and our food sources will require that the future of wastewater treatment deal with the contamination inherent in our modern lives, unless we significantly reduce our consumption of the many goods that contain these chemicals. The wastewater treatment plant always has been a barrier between the waste we produce and the environment, and we can continue to play this role. So the costs of sludge disposal, including treatment for PFAS and other contamination, have to be taken in addition to the cost to maintain our infrastructure, the needed investments that we talked about earlier due to the age of infrastructure and climate change risks. We have a lot of work to do in the next 10 years, specifically in Falmouth and Cumberland, but in the wastewater treatment industry as a whole. So that's the end of my slides. I'm open for questions. We have 5 minutes left of our dedicated time together. But I also on this slide have my contact information, and please come for a tour. This treatment facility is a publicly owned facility, and you as members of the public have access to it. So please come schedule a tour. We'd be happy to walk you through. You get the real life version with all the smells and bells and whistles that you don't get on a computer screen. Okay, let me see if,
So I can feed you a question if you'd like.
sure, now
Would
that
that
now
be
I can
helpful
see
to
the
you?
chat too. Yep.
Okay.
Go ahead.
When we see big clay pipe runoff from higher up discharging into the ocean, is that untreated like Town Landing in Falmouth or Wildwood/Broad Cove in Cumberland?
So yeah, we are still seeing a lot of those big clay pipes coming out of the ground as the coastline erodes. I didn't really talk about that too much, but we have interceptor sewers. I showed the Town Landing area. We have interceptor sewers that run along the coast the full length, almost the full length of Falmouth. And as that interceptor was run, collecting all the street sewers, there were sewers that were abandoned under the streets that were not tied into the interceptor. If those pipes are running, I would suggest that they're draining groundwater. They're not untreated sewage. I can guarantee you that. If we ever find something that's running that's questionable, we can run bacteria tests on it to confirm it's not wastewater. We have done that in the past, but going back decades now, our staff have taken a survey of the full length of the Falmouth coast and confirmed that all of the street sewers were tied into the interceptors. But we do still see the clay pipes that were never removed. They were just abandoned. So as the shoreline erodes and the wave action comes and takes some of the shore away, these old clay pipes are being exposed. I hope that
Okay,
answers that question.
excellent. I think it does. Can you comment on the status and anticipated outcome date of the pending lawsuit which Maine has joined? This is obviously needed to pay for all this technology development.
Yeah, I think the lawsuit that's being referenced is that the state's attorneys general has joined a class action lawsuit against the manufacturers of PFAS chemicals. I actually don't know the status on that. I will say that the drinking water systems have come to an agreement with, 3M and DuPont. There's one other, I think Chemours are the three big chemical manufacturers that made PFAS products. There was a big settlement for drinking water utilities. When I say big settlement, there's a lot of zeros there, but when you start talking about how many water utilities there are in the country and how much some of this technology costs, it's not going to cover the cost of it. And I expect the same thing would take place for wastewater utilities. It will be a big settlement in the billions and tens of billions of dollars likely, but it won't cover enough, in my opinion. There are some other lawsuits, and I'm considering this. I've talked to some folks in town about it. Some of our wastewater utilities in the state there's a law firm that specializes in this kind of pollution law and are suing some of the manufacturing companies directly. So that's something we're considering here. We're kind of waiting a little bit to see how that all shakes out.
So before I ask the next question, I just want to acknowledge to Catherine that we are going to get to your question, but that's going to be our last question to ask. So I'm going to skip to the next one, which is, does Falmouth have CSOs?
No. CSOs are combined sewer overflows. Basically, because of the history and evolution of a collection system, in some places the storm drainage system and the sanitary system were combined. So that's what a CSO is. And when you get a lot of rainfall, the system, it doesn't have the capacity to handle all that. So a CSO is an overflow that occurs during wet weather. We don't have that issue in Falmouth. We have had some overflows where our pump stations, for example, weren't able to keep up with all the water coming into them. That is very rare. But we're not like Portland is a big CSO community, but we're not in Falmouth.
Okay. What happens to the liquid that's separated from the sludge during the last processing step?
Yep, that's a great question. It's very nutrient rich, as you might imagine. It would be considered a high strength waste. We do pipe that back to the headworks facility and it goes back to the aeration system and back through the process. I couldn't show you every little side stream. We do have, there's a number of other systems that exist at the treatment plant. I was really showing you the big ones, but yes, we do take the liquid separated from the sludge during the dewatering step and put it back through the process.
Um, I am as interested in this as Denise is. This tour thing is very interesting to me.
Happy to do it.
Denise wants to know what ages is the tour appropriate for, and is there a smell factor?
There's a smell factor. Let me answer that one first, but only in certain portions. The headworks facility, as you might imagine, where all of that water that's been in pipes for 11 miles finally sees the light of day, there can be a smell associated in the headworks. But you can skip that part or you can brave it and come through. I mean, we do work in that area. It's not an area that requires any special protective equipment, for noxious gases or anything. We do monitor the space for gas detection. We have a gas detection system out there. But in terms of the first part of the question, I could make a tour appropriate for any age. The older you are and the more knowledge you have of chemistry and biology, it's fascinating. And we could talk about the chemistry and science behind it all day, but we can also take second graders through and they can enjoy some of the big equipment that we have and look at how we take dirty water and make it clean.
I have to tell you, I'm sort of intrigued, and I'm thinking it'd be really cool to set up a library program and everyone
Please,
meets at the
please. That's part
meets there.
two.
So
That's part two of the presentation.
stay tuned, everyone.
Yeah,
Okay. My gears are turning.
great. Love
And
it.
finally, last question. So what does the average citizen do?
Well,
What's the takeaway we should leave with?
that's great. I wanted everyone to understand the complexity of the process at wastewater treatment, both from a mechanical perspective, getting the water to us, and also the biological and chemical process that we do at the treatment plant. That being said, I don't expect everyone, obviously, to become a wastewater treatment plant operator. I will say if there are folks in your world who are looking for an interesting and productive line of work, the industry in general is, like many, always looking for people. So if you know anybody who wants to work in the field, that's one area. But I would say from an average citizen perspective, I think one of the things I'm trying to do, for many years, wastewater treatment has been seen as a dirty, as a polluter almost. And we've gotten that reputation in some of the environmental circles and the environmental advocacy groups. And one of the things I'm trying to do is change that perspective, because we are actually a barrier protecting nature from the waste that we produce. And so I think the biggest thing the average citizen can do is recognize that this is an incredible asset that the town has, and that also we are going to be in the near future coming to you with requests for significant funding, not just for the PFAS and the chemical contamination stuff, but just to deal with climate change and the capacity issues and the age of our infrastructure. So supporting your wastewater utility and your water utility, recognizing that these things are critical, but also extremely costly, and supporting us is one thing that I think the biggest takeaway.
Fantastic. Thank you. Sophia says that average citizens should advocate for regulation and elimination of chemicals in our consumer goods.
Absolutely.
That's
Thank you, Sophia. That's a great point. I mean, Maine is leading the nation on this, not just on the land application of sludge side. We also, at the state level, have a PFAS in products bill. So, and one thing we do advocate for, I'm on the government affairs committee of our regional Water Environment Association. It's the industry organization for wastewater treatment facilities. And we always are advocating for, the place to deal with PFAS and chemical contamination is at the source. It's not at the treatment plant at the end, although it's easy to sort of point your finger at us because we have a pipe that goes out into the ocean. But yes, the PFAS and products law is a phased approach to taking PFAS out of any products. That being said, I'm a little skeptical because we've come to depend on the services that PFAS provided. We all love our nonstick pans and our waterproof jackets and our stain resistant furniture. So I'm also skeptical of what are the chemicals that are coming to replace the PFAS. So it's a work in progress, but that's a good point.
excellent. Well, thank you. Um,
I see there's a
So
lot of other stuff coming in. I'm happy. My phone number's there. Please reach out to me. My email's there. And you can come anytime for a tour. Please just schedule ahead of time because we aren't open all the time.
yes, so somebody says you're as good as they get, and we are really
Oh,
lucky to
oh my
have you.
gosh. Well, how
And then
nice. Thank
somebody
you.
said that you and wait, hold on, I have to get the thing. It says you and all
You made my
wastewater
day.
folks are the unsung heroes of the world.
Oh,
But
wow.
I would say you're the unsung heroes of the underworld.
Oh, I love it. I love it. Well, with compliments like that, I think I'll take the rest of the week off.
You've got fans among the audience.
Oh,
Um,
great. Well, I'm
well,
happy about that.
thank you everyone for joining us this evening,
Thank
and
you.
a shout out to Falmouth Memorial Library for partnering with me on this presentation. And stay tuned. I will probably be sending out the recording to anyone who registered in the next few days, so you can pass it on to other people. And Dan, thanks so much. This was
Thank you, Kelly.
fabulous.
Thanks
Yeah,
everyone for coming. I really appreciate it.
thank you.
Taking some of your evening with me.
All right. Good night.
Have a good night, everybody.